And the typical approach would be to assume this virtual crystal approximation where we average aluminum gallium and make a kind of a new atom, aluminum gallium. And out of yellow and blue comes green, right? But that means, again, we homogenize the whole material. So what would happen if you have a VCA-like aluminum gallium arsenide nanowire? This would be the dispersion you would compute in this nanowire. And this is the transmission that is associated with this nanowire. So you have a bunch of bands that are out at X, a few at gamma, and for every band you get a nice little step in your transmission. Okay? Now, what happens if you have a truly alloyed nanowire? One thing you can do is you can do a statistical average and extract an average band edge. And just like in bulk, where in Al gas, a VCA over-predicts the gap at gamma, also in a nanowire, so unfolded supercell would give you a different band gap, and it would reduce the band gap. So this is a statistical band edge diagram of a nanowire. If you now computed a transmission coefficient, it is no longer very smooth, but it looks rather rugged, and it even has resonance-like features in it, little spikes. And certainly not nice steps for each band. It looks like as if there's here on the top left in red, there's one nice band, and we would like to see one or two, a perfect step, right, in our transmission coefficient. It turns out there is not a perfect step. There's somewhat of a ledge, but it's modulated in energy. So where does this come from? We can do a Gedanken experiment again, where we say, okay, we have this wire as depicted on the bottom left, and we take each slice and assume we want to compute what the band edge is of that slice if it were infinitely periodic. Then we go to the next slice and compute what the band edge would be, and so on. And we would find that the bottom of the conduction band edge in this wire is not very smooth. It's actually very rugged. We can go a step further and calculate the density of states in this wire. Density of states, dark means electrons like to sit there, light, they don't want to sit there. And you see something that resembles a resonance that sits in the middle of the system. In energy, that resonance is exactly where the spike is in the transmission. So we have a local state, a localized state sitting in the central nanowire that is resonantly enhancing the current. It's almost like a little RTD. Okay? And the interesting part is that you could relate that to some fundamental theorems that say if you have a 1D system, a wire is a 1D system, and you put in this order, you must have localization. It's called Anderson localization. Then the question is, how big in lateral dimension does your 1D system have to be for that to go away? But in this relatively thin nanowire, it is pretty clear that there's a localized state sitting in it due to this order. Comes out of the simulator by itself. It's not like we stuck it in and made sure it's there, right? It's more like we saw this transmission coefficient, looked, why in the world is it so spiky, plotted the density of states and saw a bound state. You can do something similar for silicon germanium nanowires. But it is much more messy because you have gamma points and X points that are all interacting with each other, these delta 4 values, and then you have some delta 2 values, and overall your dispersion is really, really messy. And your local band structure is not even a good predictor. So it's really messy along the band edge. If we march through the device, we would have a band edge that is really broad, and through VCA and our unfolded band structure at least give roughly the same result. And the details are in a publication on transaction on electron devices. So I want to conclude this section on alloy disordered nanowires and say that alloy nanowires are not smooth throughout the device. The conduction band edge fluctuates locally, the dispersion changes, and the transmission and the density of states show localization effects. Okay? Any questions? Perfectly clear, right?
Yes.
Yeah.
How did you consider the contacts in these calculations?
Yeah. So the question here is, how do we consider the contacts? In the calculation of the band structure, in the supercell calculation, we repeated the nanowire along periodically.
Okay, so it's periodic.
Right, it's periodic for the supercell.
Yeah.
And for the transport calculation, we assume that we have a couple of disordered cells, and then we have a boundary condition that includes a couple of disordered cells. But that means, effectively, we have an ordered contact. It's locally disordered, but then it's a repeated cell. So there's a step-like transition from the nanowire to the contact, because we can't calculate the self-energy of the whole disordered system.
It's far enough that it's not important.
Hopefully enough, yeah.